All right, so finally we're going to wrap with four related angles, four bow tie angles that have a reference angle of 45 degrees, because that's our one outstanding reference angle we haven't talked about yet, coming off of a 45, 45, 90. Let's take a look. So looking at your unit circle, notice where the reference angle is located. 45, 45, 45, 45. The reference angle sits between the x-axis and the terminal side. 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 When you want to draw right triangles, where do you draw the altitude to? The x-axis. So from the point, drop an altitude to the x-axis. From a point, altitude to x-axis. Point, altitude to x-axis. Point, altitude to x-axis. X, x, x-axis. So we got four angles, 45 degrees in quadrant 1. In quadrant 2, that's an obtuse angle of 135 degrees. In quadrant 3, that's a reflex angle of 225 degrees. And then in quadrant 4, another reflex angle of 315 degrees, right? We can see all four of them here. I've already filled out the exact tree values for this part, because this video, you've probably seen the pattern at this point when we were looking at 30 degrees and 60 degrees for a reference angle. Everything's hinging off the special right triangles. So let's think about what we know. If I take this 45, 45, 90 triangle that I've created in quadrant 1, and I move it over here, what do we know about the relationships of the sides in a 45, 45, 90? Well, we know if both of the legs are W, it's an isosceles triangle, so they're going to be congruent. If both of these are W, the hypotenuse is W root 2, okay? Well, the radius of the unit circle is 1, and that means the hypotenuse is 1. That means that W root 2 is equal to 1 unit, all right? Well, if we want to solve for W then, to get the lengths of these sides, we actually have to do a little bit of math, right? 1 equals W root 2. Take a look down here. So if W root 2 is equal to 1, then we want to solve for W. We're going to divide both sides by root 2. Therefore, W equals 1 over root 2. Can't leave a root in a denominator. To rationalize, we're going to multiply the top and the bottom of this fraction by root 2 over root 2. Multiply across the top and the bottom, we end up with W equal to root 2 over 2. This is root 2 over 2. And so is this. Root 2 over 2. It's an isosceles triangle. Two congruent legs. Therefore, look at your coordinates. Over root 2 over 2, up root 2 over 2. Both are positive. Back root 2 over 2, up root 2 over 2. Negative, positive. Back root 2 over 2, down root 2 over 2. Negative, negative. And finally, positive direction root 2 over 2, negative direction root 2 over 2. Positive, negative. So with your four related angles, when you go to evaluate the three trig functions, sine, cosine, and tangent, sine is going to be root 2 over 2. Y coordinate over radius. Radius is 1. Cosine, x coordinate over radius. Radius is 1. Tangent is going to be y divided by x. Well, if y and x are both the same value, then tangent is just going to be equal to 1. Now look at the patterns that develop throughout the rest of the quadrants. In quadrant 2, I see the same exact trig values repeat, but look what became negative. Sine remains positive because the y coordinate's positive in quadrant 2, but cosine and tangent are negative. In quadrant 3, look what's negative, look what's positive. Sine and cosine are negative in quadrant 3, 225 degrees, but tangent is positive. And think about, why does tangent become positive but the other two are negative? Tangent becomes positive in quadrant 3 because both y and x are negative. A negative divided by a negative. Y divided by x. That's going to become a positive value. And finally, in quadrant 4, look at what's becoming positive versus negative. Sine is negative root 2 over 2. Cosine is positive root 2 over 2 because your x coordinate is positive. Tangent is negative. You have a negative value divided by a positive. This is all about pattern recognition. And again, I didn't have to use a calculator for any of this. It was simply all solving based upon what I know about special rights and the way that positive and negative coordinates work on the Cartesian plane.